S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
What is basically the difference between a vapor and a gas? So the idea is to understand that can we liquefy gases at all temperatures? Is it always possible to liquefy the gases or not? Welcome to S. Chan Academy. Myself Dr. Mamta Sethi. So today I will be discussing with you about the liquefaction of gases, and we would be discussing about the factors which favors liquefaction of gases and under what conditions it can be done. So if you want to read in details about the topic, you can refer to the book by S. Chan Publishing, the link to which is given in the description box. So let us now understand the the physical conditions under which we can liquefy a gas. So basically I was discussing with you that what favors liquefaction of gases and what is the difference between vapor and gas. So basically, see, if you see, you try to understand the liquefaction in gases, we would again go back to the conditions that we try to impose on the molecules of gas. Consider a sample of gas. So on increasing the pressure, what would happen? If you increase the pressure, the gases compress, the gases would squeeze. So obviously they would compress to a smaller volume, right? And the gaseous molecules will come close to each other. The same phenomena can be observed by decreasing the temperature. So on decreasing the temperature also, as per Charles' law, temperature is what? Directly proportional to the volume, and therefore upon increasing the pressure or on decreasing the temperature, gases will tend to compress. Now when the gases compress, the molecules will come close to each other. And now when they are so close to each other that at this point of time the intermolecular forces of attraction cannot be ignored. So that means that molecules are interacting with each other. And what happens? That the next state of matter, upon increasing the pressure and decreasing the temperature, the gases tend to liquefy. So both these factors tend to favor liquefaction of gases. So who studied? Basically Andrews was the first scientist who tried to observe the behavior of carbon dioxide. He basically studied the pressure versus volume curves for carbon dioxide and came up with the conclusion that somehow temperature plays a more important role. Now herein I have mentioned that both temperature and pressure, increasing the pressure and lowering the temperature favors the liquefaction. But suppose I am trying to liquefy a gas, right? I am trying to liquefy a gas at room temperature, and let's say my room temperature is 25 degrees Celsius. So if I try to do the same for carbon dioxide, let's have a look at the curves, what kind of curves I will be getting. So let's say I start from point A. This is the point where of course the gases at lower pressure, the pressure is low, gases have high volume, right? High volume is there. Then if I increase the pressure, see, let's say I increase the pressure, what happens to the volume? The volume will decrease. The volume will decrease and therefore we will reach to a point B. Up to this point we observe a constant decrease in the volume upon increasing the pressure. Now at this point of time, if I further increase the pressure, what will I observe? That at this point of time, the gases will turn into liquid. Just now I have explained you that upon increasing the pressure, gases tend to liquefy. Now to up till point C, what do I have? I have both liquid as well as gas. So इस कर्व पे ये जो आपका स्ट्रेट लाइन है, इसमें we have both the phases. We have gas plus liquid. So दोनों phases इस कर्व में आपकी क्या है, दोनों phases exist करते हैं, right? So now most of the the pressure that you are applying is used for the liquefaction of the gases. तो आप क्या देख रहे हैं, there is not much change in the pressure. All this is happening at one value of the pressure. So volume is changing drastically. Volume change होगा because gas क्या हो रही है, liquid में convert हो रही है. जब gas liquid में convert हो रही है तो volume बहुत ज़्यादा कम हो जाता है, right? So volume has decreased a lot. Now up to some extent, whatever possible was there, the gas has already squeezed and turned into a liquid. Now here the liquefaction is what? It is completed. Now after this point, if you apply the pressure, what will happen? What did we study in the first lecture of this series? We studied that liquids are not compressible. They are not compressible. So if you apply pressure, what will happen? Here you see this kind of behavior. So pressure has increased drastically, but there is hardly any change in the volume. And this is quite obvious. This is the property of the liquid, that they are not compressible. Now this particular curve, pressure volume type curve, we can call this point as D, where the highest amount of pressure, whatever we wanted to, it has already been applied. This particular curve has been plotted, let's say at about 12.5 degrees Celsius. Now let us try to have a look at this behavior of carbon dioxide at a slightly higher temperature. Maybe we can start this curve at this point, and then again we would be seeing that a similar behavior as it showed at 12.5 degrees Celsius, it would be showing the same kind of behavior at, let's say, 23 degrees Celsius, and further at this point of time, this curve in this case would be slightly higher, like it would be slightly lengthier, right? And then we would see that the liquefaction commences at this point. Liquefaction will continue up to this point, right? We may call these points as A dash, B dash, C dash, and at this point C dash, the liquefaction is over. So the entire amount of gas has turned into a liquid. अब जब again liquid बन गया तो फिर क्या होगा? How much ever pressure you may apply, there will be hardly any change in the volume, right? So what change are we seeing at higher temperature? We see that this horizontal portion, what does this horizontal portion represent? This represents mixed phase. This has liquid phase as well as gaseous phase. The width of this portion has decreased at a higher temperature. Now for carbon dioxide, now at a slightly higher temperature, we may observe that this particular horizontal portion further decreases, right? And we may come to a point this at a temperature, let's say 31.1 degrees Celsius, 31.1 degrees Celsius, this particular portion will completely disappear, it will turn to a point and then this curve continue like this. Now, what do we see here? That as we keep on increasing the temperature, this horizontal portion is squeezing and ultimately it will turn to a point. And if I join the horizontal portion of all these curves, so at this point, so what is this point? This curve has been plotted at 31.1 degrees Celsius for carbon dioxide. So what we see here, there is no mixed phase. So for other temperatures which were below 31.1 degrees Celsius, we could see that there is gas as well as liquid. And here we see that the moment this much pressure is applied, the gas will completely turn into liquid, and above this temperature you may see that the normal PV isotherms as per Boyle's law are observed, right. So this point we define at, what do we call this point? As critical temperature. So what is so important about the critical temperature is that we see that if the temperature is above 31.1 degrees Celsius, there is no liquid phase, only gaseous phase is there. So that means the question that I asked you in the beginning of this session, you are getting the answer now. You will not be able to liquefy carbon dioxide at a temperature above 31.1 degree Celsius. It means, below this temperature, you may be, you may be getting both the phases, you may be, able to convert into liquid, but above this temperature, how much ever high pressure, see the pressure has gone from this to this, but you are not getting liquid phase. So this may be then, put it in other words, the definition of the critical temperature. And here we have also come to this conclusion that though pressure and temperature both favors liquefaction, but what is the deciding factor? The deciding factor is temperature. So temperature plays more important role, and therefore we define critical temperature for gases. So critical temperature is basically the minimum temperature above which a gas can never be liquefied, how much ever pressure, high pressure you may apply, right. At a temperature, let us say for carbon dioxide, let us say you have a temperature of 32 degrees Celsius or let us say 35 degrees Celsius. So you may tend to apply pressure of 1000 atm, but you will never be able to liquefy carbon dioxide gas, right. This is the point of difference between a gas and a vapor. So what is the difference? A vapor can be liquefied at any temperature. There is no critical temperature for vapors. So you have, for example, you have water vapors, they can be liquefied, you close the lid, you had heating, boiling the water, it is getting converted into steam, right, and then if you close the lid, you get that liquefaction happens, that condensation happens, but the same thing will not happen for gases. So for gases we define critical temperature, but for vapors there is no critical temperature. This is the point of difference between the two. Now what is critical pressure? The critical pressure is the pressure. Now at this particular temperature, let us say for carbon dioxide 31.1 degrees Celsius, certain amount of pressure is required to liquefy the gas. So in this case it was 72.8 atm. So at 31.1 degrees Celsius, 72.8 atm pressure is required to liquefy carbon dioxide, to convert gaseous carbon dioxide into its liquid form. So, this is known as critical pressure. Now, coming down to critical volume. So, what is critical volume? The critical volume is actually the volume occupied. As we know that volume is nothing but it is related to temperature and pressure via the gas equation, right. So, it is decided by the temperature and pressure that what volume gas will have. So, the volume that 1 mole of a gas will occupy at its critical temperature and critical pressure is known as critical volume. So, critical temperature is denoted by Tc, critical pressure is denoted by Pc, and critical volume is denoted by Vc. So, here in this part of the lecture, we have understood the qualitative description about the critical temperature, pressure and volume, that they exist for a gas. But how do we calculate these values? How do we get to know that for a gas, what will be its critical value? How do we know that what will be the value of its critical temperature and pressure? So, we take a small break here. So, after the break I will be coming up with the calculation of critical temperature, pressure and volume.
Hello everyone, I am Dr. Seema Thakran. Welcome to S. Chand Academy. I will be teaching you topics limit and continuity, differentiability, partial differentiation, tangents and normals, curvature, curve tracing and many more. Please like, share and subscribe S. Chand Academy, and don't forget to press the bell icon for the future updates.
So, welcome back to S. Chand Academy. So, before break I had asked you the question about the calculation of critical constants. So, together critical temperature, pressure and volume, they are called as critical constants. So, how do we calculate the critical constants, right? So, we again go back to the the van der Waals equation. The van der Waals equation can be rearranged into a cubic equation. This is simple mathematical rearrangement. You can do it yourself. You can write the van der Waals equation, rearrange the terms, and you will be getting this particular expression, which is your equation number 1. Now, we can calculate the value of critical temperature, pressure and volume with the idea that, see, since this is a cubic equation, looking at it as a mathematical problem, we know that if we have a cubic equation, we would be getting 3 roots for this. Therefore, if we solve van der Waals equation, we would be getting 3 values of volume. Now, those 3 values of volume can be all real, out of which 2 can be real, 1 can be imaginary, 1 can be real, 2 can be imaginary, and the value for the same we can calculate it by using the idea or by utilizing the fact that what will happen, that if we try to plot this cubic equation, equation number 1, we would be getting curves similar to Andrews isotherm that we had just had a look at, Andrews isotherms for carbon dioxide, with a small difference that we would be getting a curves like this, right. Instead of getting the flat portion, we would be getting a curve like this, right. And then if we draw our parallel line, so these are the 3 values, right. So, these are what? These are nothing but these are the theoretical curves as per van der Waals equation. So, as per equation number 1, if I plot pressure versus volume, I should be getting these 3 values of volume as a root. Now, what will happen at critical temperature? So at critical temperature we have already defined that this point, this horizontal portion will squeeze to a point. So what will happen mathematically? Just look at it as a mathematical problem, not as a chemistry problem. These 3 points are merging into a single point. So what does it mean? It means the roots of this cubic equation are all same. This cubic equation has same roots, equal roots. So what is the meaning? This is what? Critical temperature. So at critical temperature, what is the volume? Volume is critical volume. So V becomes equal to Vc. What happens at critical temperature? V becomes equal to Vc. Alternatively, I can write V minus Vc equal to 0. I can take cube of it and V minus Vc will become 0. Upon expanding this using the formula of A minus B whole cube, I would be getting equation number 2. So now I have 2 equations, right? One is van der Waals equation, the other equation as a special case when we put, we use this condition of having the same roots. Now this particular fact can be used in order to calculate the critical constants. So what do? Nothing special, we just have to compare the coefficients in the 2 equations. So let us say here we have V cube here, we have V cube here, V square here, we have V square here, we have V here, we have V here, and we have a constant term over here. So what do? We just compare the coefficients of V cube, V square and V in equation number 1 and 2, and upon solving we would be getting the values of solving and rearranging the terms. It's just simple mathematical manipulation. On rearranging the terms, we would be getting the value of critical temperature, critical pressure and critical volume. So we are now getting the values of these critical constant in terms of simple van der Waals constants. So A and B here are nothing but these are van der Waals constants. So therefore we can see here that critical temperature, critical pressure and critical volume for any gas can be calculated by simply substituting their van der Waals constants in these expressions. So if we substitute the value of A, R and B over here, we would be getting critical temperature for that particular gas, and therefore we can decide that what are exactly the conditions which are required to liquefy a gas. You can decide upon any gas, you can try liquefying any gas, but for that you need to do the theoretical calculation for its critical temperature, and then further extending on to how much pressure you need to liquefy that gas and what volume that gas will be occupying at that particular temperature and pressure. So this was all about liquefaction of gases, and there is last phenomena, last property that we would be studying about the molecules of gas. Again, see, we have discussed qualitatively about the collisions which are constantly occurring in gaseous molecules, but till now we have not discussed onto how many collisions are occurring, what is the collision frequency of these gaseous molecules. So let's have a look at the the quantitative picture of these molecular collisions. For the sake of simplicity, we would be considering the collisions between two molecules, that is we are considering the bimolecular collisions between the gaseous molecules. So let us say we have two gaseous molecules. As per the suggestions made by van der Waals, the gaseous molecules can be treated as hard spheres having certain volume, and therefore, so this is basically the radius of this molecule, and the molecules, they are all same, all are of mass m, and therefore their radii will also be different. Now this is the point, as we mentioned earlier also, that when the gaseous molecules will come close and close to each other, it is at this point that they would touch each other, and this is the point where the effective collision will take place. This is the point where we consider the collision between the two molecules, and therefore this distance, right, the distance between the centers of the two molecules is known as what? The collision diameter, or the distance of closest approach. So it is this distance at which we consider that the molecule, one molecule has already undergone a collision with the other molecule. Now if we say that D, so we define this D as collision diameter. If we have this collision diameter, we would like to here define the related term, which is your collision cross section. So what is your collision cross section? It is simply, if we consider that a sphere of radius d, we will be then able to have this surface area, this effective area, which is defined as collision cross section. So this is basically the region, effective target area, where the collision between the two molecules would happen, right. Now after having understood that at this point, if the distance between the centers of the two molecules is greater than d, we would not consider the collision between the molecules, and also we have to understand the fact that this is the distance of closest approach, since these two molecules cannot penetrate into each other. They are hard spheres, they cannot penetrate each other, right. So this is that's why this is known as distance of closest approach, and the corresponding target area where the other molecules can also come in and collide is called your collision cross section. So after having understood the collision between the molecules, we now have to understand that how many collision a molecule will undergo. So considering, let us say for the sake of simplicity, calculate the collision suffered by one molecule. So a single molecule per unit volume, if it is present in the unit volume of the gas, volume of the container we consider equal to V. So a single molecule in unit volume of the gas will undergo how many collisions? It is given by this number, which is called collision number and is denoted by Z1, which represents, which is proportional to basically the collision cross section. Of course, the effective collision, the number of collisions which a molecule will suffer will depend upon what factors? It would depend upon the collision cross section, it would depend upon the average velocity of the molecule, and it would also depend upon number density, how many molecules are present in unit volume of the gas. So because that single molecule is going to collide with the rest of the molecules. So this term basically represents the number of collision which a single molecule will have with rest of the molecules which are present in its surrounding, right. Now there is another coined term which is closely associated with collision number, which is your collision frequency. So what is collision frequency? It is simply, see, there is not that one molecule which we were considering is not only the one molecule which will undergo collision. All molecules are same, and therefore all these molecules are going to collide with the rest of the molecules. So, let us say for a moment we consider the collision that molecule number 1 is having with n minus 1 molecules, and then in next go we would consider molecule 2. That molecule 2 will have collision with rest of the molecules minus second molecule, and then third, and then so on. But so that means all these molecules are colliding with each other. So, considering the collisions between all these molecules, we can then define the term collision frequency. So, how many collision? Frequency means per unit time. So, how many collisions, molecular collision, total number of collisions are happening in unit time per unit volume of the gas? It will be further multiplied by how many molecules are present in unit volume. See, this is one molecule undergoing different collision, this is all molecules undergoing collisions in unit time, in unit volume. The only difference is we are talking about the collision and which one molecule is undergoing. Here we are talking about the collisions which all molecules are undergoing. You may notice that I have introduced a factor of 2 here. A factor of 1 by 2 has been introduced here because of the fact that we should not count the collisions twice. As in, if I count the collision of first molecule with the second, and then with the third, and then with the fourth, I should not, and then in the next go when I count the number of collisions of second molecule with other molecules, I should not be counting the collision of second molecule with the first one twice. So, it should be divided by 2. So, this is there, 1 by 2 factor has been introduced because of the fact that there should be no duplicacy in counting the number of collisions. After that, this is for similar, if we assume that all molecules are same, but it is not always same. We may have a mixture of gases also. Let us say consider formation of water molecules. So, you may have H2, you may have O2 also. So, collisions between hydrogen and oxygen molecules will take place. So, considering the collisions between different molecules, unlike molecules, we may then define different number densities. Let us say how many hydrogen molecules are present in unit volume, define it by rho 1. How many oxygen molecules are present in unit volume, let us say define it by rho 2, means it can be any other gas also unlike molecules. So, the same expression for unlike molecules can be written or represented by Z12. Now, this is the expression for collision frequency. Now, we all know that what is your ideal gas equation? Is it PV is equals to nRT? Remember that we are calculating all this, we are discussing this collision phenomena by assuming the fact that gases do behave in an ideal manner. So, PV is equals to nRT. Now, further using the relationship between R and Boltzmann constant. So, what is R? R is basically written as the product of Avogadro number and Boltzmann constant. The small k here is what? Boltzmann constant, right. So, R here is your Boltzmann constant. Using the fact that we can split this term R into Na multiplied by Boltzmann constant, we can further write pressure is equals to N into Na kT by V, and this product N into Na is what? Na is Avogadro number, N is number of moles. So, it becomes the total number of molecules which are present in the gas. So, therefore, it then becomes P is equals to NKT by V. How do we define N by V? What is your N by V? Total number of molecules per unit volume. It can be called as density, number density, right? So, rho is equals to, from this particular expression we get rho is equals to P by KT, pressure upon Boltzmann factor into temperature. So, this particular value of rho can be inserted into the expression for Z11 and Z12 and also in the expression of Z1, and therefore we would be getting the expression of collision number and collision frequency like this. So, this particular expression of collision number and collision frequency basically gives you an idea that at a particular temperature and pressure, a particular sample of gas will undergo how many collisions in unit time per unit volume. And what are the factors upon which it depends? It depends upon the collision cross section, it depends upon the average velocity, and here we have converted this into pressure and volume so that we can highlight the importance or relationship of pressure and temperature to the number of collisions which are taking place. Another important quantity, which is again related to the collision phenomena, which can be further written with the help of collision number, which is closely related to the collision number, is mean free path. So, how do we define mean free path? Mean free path basically is defined as the distance travelled by a gaseous molecules between two successive. So, it is undergoing one collision, after some times it is moving in the other direction, undergoing the next collision. So, between this one collision and the next collision, how much distance a molecule covers is called as mean free path, the distance travelled, and it is related to Z1 by this equation. So, substituting the value of Z1 from the previous expression that we have just derived, we get this particular relationship between mean free path and pressure. So, again, fix the temperature. If you fix the temperature for a particular molecule, K is fixed, T is fixed, pi is fixed, diameter is fixed, at a particular temperature even average velocity is fixed. So, what is the factor which is varying? Is the pressure. So, this particular fact or the conclusion that we are deriving here is that mean free path is inversely proportional to pressure, is very much useful in the practical, it has practical applications as in how to create a good vacuum. So, in case we can see here that if the pressure is small, mean free path is large. If the pressure is high, mean free path is low. So, mean free path we can say, let us understand it with the help of diagram. Suppose a gaseous molecule is here and next it is undergoing a collision. Between these two collisions, it is travelling a distance lambda. Now, if I increase the pressure, what would happen? If I increase the pressure, volume would squeeze and the mean free path will be lesser. That means molecules will have to travel lesser distance in order to undergo the next collision, right. So, what would happen? That the molecules, they will suffer many collision before reaching the wall, because lambda is small. So, many collisions they will suffer. So, at a pressure of let us say 1 atm, 1 atm is considered as a good significant pressure, right, compared to the vacuum. So, mean free path is very small, but for a good vacuum 10 raised to power, which is about 10 raised to power 3 atm, the pressure for a good vacuum is approximately this much. So, at such a lower temperature, mean free path is very high. So, that means the molecule will travel it will travel less number of times before reaching the walls and before contributing to the pressure, and such type of gas where lambda is very high is called, this concept is known as Knudsen gas. This particular sample is called Knudsen gas. And the last property, which is again a very important property, which is related to the the calculation of the mean free path, is your viscosity. So, we all know that fluids, they have viscosity. So, viscosity arises in gases because of the transfer of momentum. Now, viscosity of gases according to Chapman's equation is related to lambda. So, again try to form a link that we calculated the number of collisions, collision number, we related the collision number to mean free path, and now we are relating that mean free path to viscosity. Viscosity is related to mean free path like this, and inserting the expression of lambda over here, we find a very important equation wherein we find that viscosity is proportional to T raised to power 1 by 2. So, that means we can say that viscosity is directly proportional to temperature for gases, which is a very unusual thing if we compare it to that of the liquids. Generally, we know about liquids that viscosity decreases upon increasing the temperature, but it is reverse for gases. So, as we increase the temperature, viscosity also increases. So, this increase is because of the fact that at higher temperatures, the molecules carry higher momentum. The rate of transfer of momentum is higher in case of gases, and it is the transfer of momentum which gives rise to the existence of viscosity in gases. Therefore, we can say that this opposite trend is observed for gases, in case of gases, the dependence. So, this explains the dependence of viscosity of gases on temperature. So, with this we conclude this session. So, in this particular session we have understood about the quantitative expression for the the collision phenomena, rather we have discussed at length, and we have also discussed that how the viscosity of gases depends upon temperature. So, if you want to read in details about the topic, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. Kindly like, share and subscribe, and do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.